Okay, morning, everybody. We're going to go ahead and get started. So last class, trying to think of what class you are. Yesterday, we were talking about Ohm's law. Okay, so we were going through some of the Ohm's law calculations, E equals IR and P equals IE. And we're going to get lots and lots of practice using those formulas over the next couple of weeks, the rest of the semester and the rest of your schooling. What we're going to do today is we're going to start applying those. So we're going to look at series circuits first. Series circuits being one of the easiest to understand and certainly the easiest to do the math on, even if it's not the most common series, not the most common circuit. So we're actually going to use parallel a lot more, but we got to start somewhere. So series is an easy one to start with. So we'll start there. Okay, so solving series circuits. So a series circuit, remember we talked a couple of classes ago about what a series circuit is. Series circuit has only one path for current to flow. So I can have more than one electrical load or electrical device, but there is still only one path. So what that means is that the same current passes through all of the devices. Okay, every device and including the source all have the same current. It's the same at all points in that circuit. The voltage drop in each device is going to add up to our source voltage. Okay, so if I only had one device, I showed you in the little animation where I drew the circuit, I built that circuit and we measured with a voltmeter, I will drop all of that voltage across each of the devices, most of it being across the actual device in the circuit, some of it in the wire, but usually it's virtually insignificant. Okay, so again, try and sum this up. So a series, there's one path for the current to flow. The current is the same at all points on the circuit. Some of the voltage is dropped at each device, and our total resistance increases as more devices are added. Okay, so resistance being opposition. So if I was trying to walk this path and I got to this resistive light bulb, that would have a certain amount of opposition. If I then had another one that I had to go through, that would increase the opposition. Okay, having to go through both is going to be twice as hard as only having to go through one. So my total resistance increases as I add more devices. So let's talk a little bit more about this voltage drops. Okay, so electrical circuits, you can think of them as though they're self-balancing. Okay, they're never out of balance. They always draw. Remember, we said that loads draw power, sources don't push power. So the loads will only draw what's available from the source based on their resistance and what the voltage is. Okay, we're not trying to push it with the source, we're drawing it with the loads. So whatever my total voltage is from the source is going to be divided up based on the resistance of each of the loads. Okay, in this case, we can see I've got different size resistors, a 10 ohm, a 14 ohm, a 16 ohm, and an 8 ohm. And if I took a voltmeter and I measured across each of those resistors, because they're in series, I'm going to split this 24 volts from the source amongst these four resistors, but not equally, because they're not equal resistances. If they were all 10 ohm resistances, then we would split the voltages equally because they're the same, but they're not the same. So my highest resistance, this one down here, that's 16 ohms, okay, is going to be the hardest to get through. So it's going to take the most force to push current through that resistor. Well, force electrically is voltage, right? Voltage is the electrical force that moves electricity. So if it's going to take the most force to push through this high resistance, that's where we're going to lose the most voltage. And you can see I'm dropping 8 volts there, where all of my others is less. So the 14 ohm is only 7 volts, the 10 ohm is only 5 volts, the 8 ohm is only 4 volts. My smallest resistor, so I've got a 10 ohm, a 14, a 16, and an 8. So my smallest resistor, my lowest resistance, is going to be the easiest one to get through. It's going to lose the least amount of force, or it's going to take the least amount of force to push through this resistor. So we're going to lose the least amount of voltage here. Okay, 4 volts. We're going to drop 4 volts across the 8 ohm resistor, less than all of my other resistors. Okay, and you can see this 8 ohm resistor is only half of the resistance of the 16 ohm. So it's only dropping half of the voltage. Okay, so half the resistance, I drop half the voltage. I've got a 16 ohm and an 8 ohm. So the 8 ohm is only half of the resistance. I drop 8 volts across the 16 ohm resistor. So I'm only dropping half that across the 8 ohm resistor, and we're only dropping 4 volts. Okay, and that relationship is going to be kind of the same. If you do the mathematical relationship, it's going to be the same for all of the resistors. It's really easy to see on these two because it's exactly half. And if we add up all of these voltages, I'm going to end up with 24. Okay, so 7 and 8 is 15, and 5 is 20, and 4 is 24. So all of my individual voltage drops will add up to equal my source voltage. Okay, an electrical circuit will always drop all of its voltage through the circuit. Whether I have 4 resistors or 1 or 1,000, it doesn't matter how many I have. I'm going to end up dropping all of this voltage throughout the circuit. Okay, so we're going to solve a circuit here. We're going to try and solve this circuit, and in solving it and working through the math, basically what it's going to be is we're going to be using Ohm's law, okay, our 2 Ohm's law formulas to solve this. And at the end, we're going to go through and we're going to try and see if it makes sense. So it's more important that you understand how the circuit works than it is that you get the right answer on the calculator. Okay, yeah, it's important that we get the right answer on the calculator, but you need to understand the way the electricity flows. That's going to be far more important and far more useful. So what we're going to do, and this is going to be a method for solving all the circuits. Every time we give you a circuit, there's a kind of a technique or an order that we're going to use to do this if it's at all possible. So what we're going to do is we're going to try and solve our total values first. Okay, so I've got this circuit. It's got a 12 volt source, 3 resistors, a 2 ohm, a 2 ohm, and a 3 ohm. And we're going to try and solve for whatever total values that we have. And the way we can think about that is my total voltage is basically my source voltage. So we can think about our totals as what is the source going to see. Okay, so what are all of our current needs to be provided by the source, all of our voltage needs to be provided by the source, all of the power needs to be provided by the source. So we'll think about our total values as though they're the values there at the source. So we want to solve for our total values. We've been given the voltage already, so we don't need to solve for that. We're going to start, and I'll show you how to solve this. So we'll go to the whiteboard. Okay, so there's our circuit. So I've drawn it a little bit differently just so I can get a resistor on each side, but it's the same thing. I've got a series circuit, 12-volt source. R1 is a 2 ohm resistor. R2 is a 2 ohm resistor, and R3 is a 3 ohm resistor. Okay, so we were given E total as 12 volts. That was our given. I can solve for R total because I know that in a series circuit, as I add more resistors, it just increases my resistance. So it's actually just additive. So my R total in a series circuit is going to be R1 plus R2 plus R3. So that's going to be 2 ohms plus 2 ohms plus 3 ohms. Is 7 ohms. Okay. So that's our total. Total resistance, 7 ohms. Now, sticking with the idea that I want to try and solve for my totals, the next thing that we can solve for is I. Okay. Remembering that I had those two formula triangles, E equals IR and P equals IE. So if I want to solve for I, I've got a total voltage here. We've got our total voltage and I've got my total resistance. So I have voltage and resistance. I can solve for I. So I equals E over R equals 12 volts divided by 7 ohms. Gives me 1.71 amps. So that's my I total. So what I've got here is I've got I. That's my I total. So the source is putting out that I of 1.71 amps, but this is a series circuit. So the current that comes out of the source, because I only have one wire, I only have one path, it's the same current through R1, it's the same current through R2, and it's the same current through R3. I only have one path. So that is our current everywhere, is 1.71 amps. So my last total value is going to be power. Pi formula, P equals IE. So 1.7. .71 amps times our voltage of 12 volts. Gives me 20.52 watts. Okay, so those are our total values. Now, individually, if I wanted to solve at R1, so I know what the resistance is, we were given the resistance. Yeah, we're going to try and round to 2 decimal places most of the time. I don't get too bent out of shape about rounding, because what we're going to end up doing with a lot of these numbers is I'm going to take that number and go to, for example, table 2 in the code book, like this number. Okay, so we solve for current. What I do with that current number is I'm trying to solve for wire size. So I would take that number and I would go to table 2. And my choices on table 2 are 15 amp wire, 20 amp wire, 30 amp wire, 45 amp wire. So whether I rounded it to 2 decimal places or 14 significant digits or whatever your other teachers have been hassling you about, I don't really care. because what we're doing is like a ridiculous amount of rounding once we go to the code book with it anyway. So once I go shopping, ultimately all of this stuff we're solving. And then once I have that number, what I have to do is go shopping with it. So I can only pick what's in the catalog. I can only pick what's in the code book tables, or I can only pick what's on the shelf at the supplier. So yeah, the answer is yes, we're going to try and keep it to 2 decimal places. The really short answer is I'm not going to get that bent out of shape about it. Okay, so we were given R1 of 2 ohms. I know what the current is there. This current is the same as it is everywhere. So the current at R1 is this 1.71 amps. That's what's happening here. Everywhere that red arrow is, that's that 1.71 amps of current. So I really only have 2 things to solve for. The voltage drop, if I was to take a voltmeter and measure across this resistor the way I did in that animation the other day, what would the voltmeter read if I tried to measure across this resistor? So let's do that. So at R1, we want E1, which is the voltage at R1. E equals, so what values do I have? Well, we were just talking about it. I have the resistance and I have the current, and I want to try and find the voltage. So here I want to try and find the voltage. I have the resistance. I have the current. So if I cover the E in the triangle, I'm left with E equals IR, which equals 1.71 amps times 2 ohms is 3.42 volts. Okay, so that's E1. I want to find the power. So how much heat is were we actually making at R1? So P1 equals IE is 1.71 amps times, we just solved for this, 3.42 volts. Gives me 5.85 watts. Okay, another way to do this, remember that wheel that I showed you? We've got 12 formulas that we can use. I got 12 formulas that I can use. And a good habit to get into when we get into a perfect example is a calculation like this, where I've got lots and lots and lots and lots and lots of calculations that I'm doing, is to try and use my given values as much as I can, because I know these are right. Okay, this number that I just solved for E, I've had to solve lots of things. I had to solve for I to be able to get it. And so I've had to kind of double solve. I've got 2 layers of solving I had to do to get this E1 number. So first of all, I'm incorporating more rounding error, but more importantly, if I made a mistake on I, then I've compounded that mistake here. So to try and use our given values as much as I can, sometimes I can't use nothing but given values, but at R1, I was given R. So one of the formulas we derived yesterday was P equals I squared R. Okay, so 1.71 squared times 2. .85 watts. So the math will always work. As long as we're doing the math correctly, I'm always going to get the right number. It doesn't matter which formula that I use, But this P equals I squared R would be a better process. Okay, it would be a better way to use the numbers, because in P equals IE, I've had to solve for I and I've had to solve for E. So I'm using two values that I may have made a mistake on, where in this one, I've only had to use one that I've had to solve for, where R was a given. It was just here, it was 2. So there's less chance of an error, of me having made an error, or there's less chance of me using a number that I've made an error on if I'm using a formula like this. Okay, so not mandatory, but it's a good practice to get into. Okay, so that's R1. So if I took a voltmeter and I measured across R1 with a voltmeter here, like that, that voltmeter would read 3.42 volts. That's how much voltage we would be dropping across that resistor. Okay, so if I solve at R2, E2 is what? I don't even need to pick a calculator up for this one. What's my voltage drop at E2? Right on, same thing as R1. If my resistances are the same, and my penmanship is not good, 2. So I had 2 ohms at R1 and 2 ohms at R2. Well, if their resistances are the same, then their voltage drops are going to be the same. So if I drop 3.42 volts at R1, that is what I'm going to drop here too, 3.42 volts. Okay, if you don't believe it, do the calculation. So E equals IR, 1.71 times 2, which is exactly what we did here, 1.71 times 2. So the answer's got to be the same, 3.42 volts. And my power then, guess what? Same current, same voltage. My power is going to be the same at 5.85 watts. Okay, I would just be writing this formula all over again with exactly the same numbers. Okay, so R3, my voltage drop, E equals IR, is 1.71 amps times 3 ohms. Is what, 5.13, I think. .13 volts. So that's my voltage drop at E3. Now, my voltage drops need to add up. So this is my final check. Okay, I can close this circle and verify, say you're doing a test or something. I don't need to guess at whether I'm doing the questions right. I don't need to wait until we get the test back to know whether I got them right. I know that all of my voltage drops need to add up to equal my source voltage. So if I add up 3.42 and 3.42 gives me what, 6.84, and 5.13, that's 11, well, with the rounding, that's pretty damn near to 12. So I know I did that right. I just proved it to myself. If all my individual voltages add up to my source voltage, I must have done it right, or there's a pretty good chance I did it right anyway. Okay, so P3 I, P equals IE, so 1.71 amps times 5.13 volts. P3 is 8.77 watts. Okay. And same thing, we solved here for my total power, 20.52. If I add these up, 5.85 and 5.85 gives me 11.7 and 8.77. So 19, 20 point something, 20 point something, close to 0.5. So we're pretty close there. Okay, again, it's not exact because we've incorporated by rounding error when we started way back here with the I by rounding this to 1.71. So every time I use it, and we've used it in every single calculation, every time I use it, I incorporate that rounding error, make it a little bit larger and a little bit larger. Okay, like I said, that's close. Even just doing it in my head, I'm like within 0.5. Okay, that's proved to me that we're doing it right. So we started here with our total values. Okay, E total we were given, R total we solved it because it's just addition. We solved for I, we solved for P. So those are our 4 values. We solved for the total values. And then I went back in R1, we were given the resistance. We knew what the current was because current stays the same in a series circuit. Solve for power. And then at R2, solve for a voltage drop, solve for power, solve for voltage drop, solve for power. And then I went back and double checked. Okay, close the circle, close the loop, make sure that all these individual ones add up to what our totals were. So I can do that with voltage, I can do that with power. Resistances we were given and current is the same anyway. Okay, so totally and completely confusing, right? No idea how to try and organize yourself and do this. Where do I start? What do I solve for next? I don't remember what values I have. I don't remember where I need to go. So let me give you a tool here. I'm going to give you something as a tool, and whether you use it or not is entirely up to you. It's like me giving you a power saw. If you want to use a hand saw instead of the power saw, well, there's not much that I can do about that, but I'm going to try and give you something to get organized. So let me get rid of this. I really wish they had a clear all function on this whiteboard. What we're going to use is something for you to get organized. And all it is a table. This is just a visual tool to try and help you figure out what you're trying to do here. So what I'm going to use is wire. W-I-R-E. Okay. This is actually P for power, but pyre doesn't spell anything. So wire is easy to remember. Okay. Watts for power, I for current, R for resistance, E for voltage. Okay. Easy enough. What I'm making here is I'm going to make a table. And down the right, the left-hand side, what I'm going to do is I'm going to put all my individual devices in. So I have resistor 1, resistor 2, resistor 3. So I'm going to write them down the left-hand side. Resistor 1, resistor 2, resistor 3, and then I'm going to make one called total. Okay, so there I have a table. Now, to use this table, if I move back and forth through this table this way, if I'm moving side to side in this table, we're using one of 2 Ohm's law formulas. Okay, so, right, P equals IE, E equals I times R. So if I'm moving back and forth left and right through this table, horizontally through this table, I'm using an Ohm's law formula, one of the 2 of them. If I'm moving vertically through this table, I'm using what are called series circuit rules. Okay, so what's a series circuit rule? I'll come back to that in a second. When we were solving that circuit, we determined that our I was constant, okay? That's what we were using. We know that there's only one path, there's only one wire. So no matter where I measure the current in that wire, the current has to be the same. This is really important. You need to write this down because this is the key to solving the circuit. My resistance is additive. So the more loads that I put in, the more resistors or light bulbs or whatever it is, more electrical loads that I put in, it's just going to add to the total resistance in the circuit. My total voltage is additive. So all my individual voltage drops add up to my source voltage. And my power is additive. So all my individual powers at my individual devices add up to my total power. Okay, so my current is the same. My current is constant. Everything else is additive. So those are the rules that I'm going to use if I move up and down through this table. This isn't going to help you do the calculations, but this is going to help you see what values you have, and it's going to help you see what you can solve for. Where are you going to go next? So every single value that we solve for or were given that we had just finished filling this whiteboard with, I'm going to write down in this table. Okay, so I'm going to write down what I was given in red, just to try and distinguish because color helps. So I was given my total voltage was 12 volts. I was given R1. So my resistance R1 was 2 ohms and at R2 was 2 ohms. My resistance at R3 was 3 ohms. Okay, so those are my given values. Now you can see I've got all my individual resistance values. The only thing that I've got left here is my total value. And I know that resistances, because of series rules, when I move up and down through the table, resistances in a series circuit are additive. So if I just add these three together, 2 and 2 is 4 and 3 is 7. Okay. We solve for that over here. My resistance total is R1 plus R2 plus R3 is 7 ohms. So I've got that here, 7 ohms. Okay. Now that I have two values horizontally, I can move through my total values using Ohm's law. So if I solve for current, right, I equals E over R using our triangle. So now I can solve for my total I, which we did. No, I erased it. Okay, I equals E over R, which was 12 volts divided by 7 ohms, gave me 1.71 amps. Okay, and my total power P equals IE was 1.71 times 12 volts. We can see that here. P equals IE 1.71 times 12. That was 20.5 something. I don't remember. 2, I think. Okay, so there now I filled that totals column, and that was where we started. Now individually, we filled this column. I filled this column. Where else horizontally or vertically do I have two numbers line up so that I can solve for another one? Well, I don't. But I do know something in this table that will help me carry on. And it has to do with the series rules. And a couple of you have guessed it at it already, right? My currents are the same, okay? So that's the key. One of the things in the series circuit is that thing that's the same really helps me because it opens this table right up. It opens all my calculations right up. I don't even need to pick the calculator up. I solved for it already. 1.71 amps. Current in a series circuit is the same. So I'm going to get 1.71 at every resistor. Okay. Over here, I've got the same current at R1, this 1.71 amps at R2 and at R3. So my current is the same, and that's where I write it in there. Now, for Ohm's law, moving horizontally through this table, I've got two values here. I can solve for E and I can solve for P, my power, just by using Ohm's law. So E equals IR will give me all my voltage drops. P equals IE or P equals I squared R will give me all of my powers. Okay, so you still need to come up with your Ohm's law formulas, these formulas, using your triangles. But this table helps you get organized. It helps you see what you have. It helps you see what you can solve for. What values do I have that I can solve for? And it's the same thing in this directionally. So horizontally, as we move through this table horizontally, we're going to use Ohm's law, one of these two formulas. And if I'm moving vertically, I'm going to use series rules. And always for a series circuit, always try and solve for current anywhere that you can as soon as you possibly can. Because with current being the same, that's going to fill this column in no matter where I solve for it. Okay, I'm going to end up with all of my current values being accessible for my calculations. Okay, so these are super important, these four things. Series circuit rules. I is constant, or I is the same, if you want to think of it that way. Resistance is additive, voltage is additive, power is additive. That's going to help me solve these circuits. Okay, so if we go back, now I've erased a bunch of my individual values, but I should be able to tell just by looking at it which resistor had the highest power drop. Well, this resistor has the highest resistance, so it's going to have the highest voltage drop. And since my currents are all the same, R3 is going to have the highest voltage drop, which means it's going to make the highest power. Okay, again, when we're talking about resistors, think about it as though it's friction. So if I have the most resistance, I'm going to get the most friction. I'm going to get the most heat. I'm going to get the most power at my highest resistor. So where am I going to use this circuit? Well, I'm not going to power anything with it. Okay, we've talked about this a couple of times. So if I had a classroom full of light bulbs and I powered them with a series circuit like this, if I had this one light bulb burn out and I have a hole burn in the filament and this light bulb goes out, well, that opens hole in the filament gives me an open in this circuit, and it's going to turn the circuit off. So if I blow this middle light bulb, all the light bulbs go out. Okay, which first of all means if I had 40 light bulbs in the room and I burn out one light bulb and all the light bulbs go out, well, that's not very useful. Okay, I would like to have 39 light bulbs on more than no light bulbs. The other problem that it causes is with all of the light bulbs out, how do I know which one of the 40 actually had the problem rather than all of them being off? Now I got to go through with a meter and I got to pull out every single light bulb and meter it out to see whether it was blown or not. So that's a problem too. So we're not going to use series circuits for powering stuff. Yeah, some Christmas lights are like that. It used to be like that, and now with the new LED lights, it's kind of the same. When you get one burnout, they all burn out. You end up just having to throw the whole string away. Okay, so we're not using this for power. Where we are going to use this is we're going to use this for control circuits. Multiple devices in series. If I have any single devices operated, it's going to trigger my result. What we're talking about is like stop buttons or switches. Okay, so if I have a stop button and I trigger that button, I wanted it to stop whatever it was powering. That's why we called it a stop button. Okay, so I might have around a line, around a manufacturing line, I'm going to have on both sides of the line And all the way up and down the line, I'm going to have these stop buttons. But the stop buttons are all going to be wired in series, so that if anybody hits one of those stop buttons and it opens the circuit, it's going to turn the machine off. It's going to turn the line off. So that's why I use them in control circuits. I use them in control circuits for that reason. The same reason that I don't want to use it to power light bulbs, I do want to use it as a safety device, as a control circuit. Okay, so stop buttons and switches, any one of them. Same thing with a three-way switch. So I've got a switch at the top of the stairs. I've got a switch at the bottom of the stairs. They're actually wired in series before it goes to the light. So if I turn either of those two switches off, either the one at the top of the stairs or the one at the bottom, if I turn either one of those off, the light goes off. Okay, I don't want to have to go down to the bottom of the stairs, turn that switch off, and then go all the way to the top of the stairs and turn that switch off before the light turns off. I want it to be any one. So it goes back to the second statement. If any single device is operated, the result is triggered. Okay, stop buttons and switches. The other place that I'm going to use a series circuit a lot is multiple sources. So multiple voltage sources. If I connect them so they all have the same polarity, I'm going to increase the voltage. Okay, so batteries, we use that all the time in like remote controls. I put more than one battery in it. Those batteries are connected with the plus to the minus. So that is an increase in the voltage. So it bumps the voltage up. The other place that we're going to use it is to power homes. You ever notice that nobody seems to be able to make the perfect app? So the whiteboard that comes with Zoom has a clear all function, but every time I touch it with my hand, it changes to a different screen. The Microsoft one seems to work better, but it doesn't have a clear all on it. Anyway, okay, so multiple sources. So what we're going to do in a house is I'm going to use multiple transformer windings. And each transformer winding is going to be 120 volts. Now, why didn't that work? So multiple transformer windings. So I've got one transformer winding, that's 120 volts. I'm going to connect another one to it in series. So I've got one wire here and the other wire here. That is also a 120 volt winding. And what that does is gives me $240 volts. Okay, so between the line 1 and the line 2, I've actually got 240 volts there. This one, and you're going to learn later on why that's called a neutral, that allows me to only use either the one winding, so between line 1 and neutral, I get 120 volts, or the other winding, so the line 2 to neutral gives me 120 volts. But if I use both windings connected in series, it gives me the voltages added of 240 volts. So that's how we power houses. Okay, so we do that all the time. We're constantly connecting transformer windings in series to try and increase the voltage or decrease the voltage. Batteries and transformer windings all the time. Okay, so that's where I would use the series circuit. I'm either going to use it as a control circuit for devices, or I'm going to use it for voltage sources. Probably one of the most common places we're going to use a series circuit is actually for voltage sources to increase the voltage. Okay, so here's an example of voltage sources. Okay, multiple 6-volt batteries. So 1, 2, 3, you can see they're connected plus to minus, but if you look at it overall, all the pluses are on the right side, all the minuses are on the left side. So connecting it in series means connecting the positive of one battery to the negative of the other, positive of the next one to the negative of the next one, and that puts them all in series so that the power has to go through all of those batteries, and then I go and power the load. Okay, so if I had multiple, in this case 4 6-volt batteries powering a 10 ohm load, and we went and solved that, okay, so 6 volts, each battery is 6 volts. So E total equals E1 plus E2 plus E3 plus E4, because I know in a series circuit, my voltages are additive, right? Those are series circuit rules. So 6 plus 6 plus 6 plus 6 gives me 24 volts. My current, I equals E over R. So I've got 24 volts divided by 10 ohms gives me 2.4 amps. And my power, P equals IE, 2.4 amps times 24 volts. $57.6 watts. So if I was to take a voltmeter and I was to measure across this resistor, what would that voltmeter read? What would the voltage drop be across that resistor? Right on, 24 volts. Okay, this hasn't changed just because I've got multiple sources. So I've got 24 volt source, but I've only got one load. So I have to drop all of this voltage across, well, I've only got the one load. So I've got to drop the 24 volts there at my load. Okay, that's where it all goes. Okay, so this is an example out of the chapter. So now I've got 4 resistors. Okay, 4 resistors, 40 volts, 100 ohm resistor, a 250, a 150, and a 300. So before I even pick the calculator up, before I draw my circuit out, before I draw my table and everything, before we do any of that, which one is going to have the highest voltage drop? Which resistor will have the highest voltage drop? R4, right. Okay, highest resistance, I'm going to have the highest voltage drop there. It's going to take the most force, the most voltage to get through that resistor. So which one's going to have the lowest voltage drop? One. What is the relationship, or how much lower is the voltage drop at R1 going to be from R4? What's the relationship? What factor difference is the voltage drop's going to be between R1 and R4? Right, a third. So you think about it, either I've got 100 ohms at R1 and 300 at R4. So either R1's voltage drop is going to be a third of what it is at R4, or the voltage drop at R4 is going to be 3 times higher than what it is at R1. Okay, 3 times more resistance is going to mean 3 times more voltage drop. Okay, and power. So in a series circuit, my currents are all going to be the same, and P equals I times E. So if I is the same everywhere, now my powers are determined by my voltage drops. So if I'm going to have 3 times the voltage drop at R4, I'm going to have 3 times the power at R4 than I had at R1. Okay, so once I solve for R1, there's a couple of different ways I can do this. I can go through and do Ohm's law for everything, or I can just have a look and go, okay, the voltage drop at R2 is going to be 2.5 times what it was at R1. The voltage drop at R3 is going to be 1.5 times higher than it was at R1. And the voltage drop at R4 is going to be 3 times more than it was at R1. Okay, math is math. As long as I'm doing the math correctly, and as long as I'm doing the calculations correctly, it's going to work. It doesn't matter which type of math I'm looking at or which type of math I try and decide. Right, so R3 is 150 ohms, and that's half of the resistance at R4. So the voltage drop at R3 will be half what it is at R4, and the power will be half at R3 what it is at R4. Okay, so let's go solve these. So 100, 250, 150, 340 volts. Let's see if I can remember any of that. Okay, so this example is in your textbook in chapter 6, example 6.1. So the textbook actually works this out longhand as we're going through it here. Okay, so I want to solve for my totals first. Now, if you want to, we can use the table. So I can throw this table in here. So I've got R1, R2, R3, R4, and my total values. Okay, and I can make my wire table. W-I-R-E. I may have made these too small to write in. Okay, so given values, R1 is 100, R2 is 250, R3 is 150 and R4 is 300 ohms. And my voltage is 40 volts. Okay, so we're going to start with totals. So there's an easy total to start with, my total resistance. Okay, so R total equals R1 plus R2 plus R3 plus R4 equals, what do we got? 350, 450, 500, 300 is 800, gives me 800 ohms. Okay, remember, as I'm going through these, if I write down something that you think is wrong, speak up, because I do that sometimes. We'll say I do it on purpose, just for laughs. Okay, so 800. So now what? Now what am I going to do? Well, let's finish with the total. So if I work back and forth across here, remember, as I work this way, I'm going to use Ohm's law when I work horizontally through there. So I can solve for I, right? So I equals, what have I got? I've got E and R. So I equals E over R. Gives me 40 volts divided by 800 ohms. Gives me 0.05 amps. Is that right? That right? 0.05 amps. Well, that's what the calculator says. Is it actually right? There we go. That's not quite right. You missed a zero there. So I'm going to move this. I got to put this in engineering notation. So I can't just have this decimal hanging out there. I got to move it 3 decimal places. So 1, 2, 3 is going to be 5 with a 0. So 50 milliamps. Don't forget the engineering notation. So 50 milliamps. Now, that is the format I want the answer written. This is your table to try and help you with your calculations. So what you do in your table is entirely up to you. And I would completely understand, because I'm never going to see your table, if you wanted to keep this as amps and put 0.05 in there so that you know what number to type in the calculator, that's up to you. I'll never see your table. Okay. To be honest with you, that's just probably something I would do myself, is to put the number in there that I actually need to enter in the calculator. Because if I write 50 milliamps up and through here in this table, every time I go to use that number in my head, I'm going to have to convert it back to a decimal number to type it in the calculator. Okay, unless you like having your calculator, you can set your calculator actually to read an engineering notation, but you still need to type it in with the decimal place. So I want you to remember this engineering notation. Your answers that you give to me need to be in the proper engineering notation, but this table you're not giving to me. This table is for you. Okay, so I'm going to leave that as 0.05 because that's how I would actually write it in my own table. And then the last one is power. So P equals IE equals 0.05 times 40 volts is 2, I think. 2. So 2 watts. Okay, everybody follow so far what we're doing? Now what? I don't have any more numbers lined up for me to do any more calculations with. What do I do now? It has to do with what goes on this way. Yeah, current, right? So remember, my current I is the same everywhere in here. 0.05 amps, 50 milliamps. Right? It's the same everywhere. So I can just write those in. So I'm just going to take that number and I'm going to write it in all the way up here. 0.05, 0.05, 0.05, 0.05. Okay. Now the rest is easy. Now I've only got 3 values in my formulas and I've got 2 numbers. So going this way, I can solve for my voltages. E equals I R. Okay, so my first one is going to be 0.05 times 100. Okay, that's easy. I'm just moving the decimal places over. So that's going to be 5 volts. And I'm going to do that for all of them. 0.05 times 250 gives me 12.5 volts. 0.05 times 150 gives me 7.5 volts. And we said the 300 ohm resistor, the voltage drop is going to be 3 times what it was at the 100 ohm resistor. So it should be 15 volts. If you don't believe me, do this. 0.05 times 300. 0.05 times 300 is 15 volts. Okay, doesn't matter how you do it. If you wanted to keep doing it with Ohm's law because it's in your head and it's easy to do because it's repetitive, that's fine. It doesn't matter. You do it however you want to do it. However, it's easiest for you to understand. We all think different ways. So however you think about it is the right way, as long as you're getting the right answer. So we made a bunch of predictions, right? My voltage drop at R1 was going to be a third of, or let's say it this way, my voltage drop at R4 at 300 ohms was going to be 3 times what it was at R1. Is it? Yes, it is. 15 versus 5 at R1, so 3 times higher. And then my voltage drop at R4 was going to be 2 times higher than it was at R3 because the resistance is twice as high. So R3 twice of 7.5 is 15. So yes, it does. My final check is, do all these voltages add up to equal 40? So 12.5 and 7.5 give me 19, 20, 25, 40. So it does exactly 40 volts. Okay, that's my double check. I know that I'm right because I just closed the loop on it. I just closed the circle on those calculations, right? I came down, I went around and come back, and I ended up closing the loop here. I sort of made a big, I don't know what you call that, a J or something, I guess, a spiral, come down and around and back down. And then I ended up, these voltage drops added up to be 40. So it must be right. So what I've got left then is to work this way and find my powers. So P equals however you want to do it. You want to use I squared R, that's fine. You want to use P equals IE, that's fine too, whichever. P equals IE is going to be 0.05 times 5 volts. Is going to give me 0.25 watts, which is 250 milliwatts. So I'm going to write these in here like that because this is sort of our last place to do it. So 250 milliwatts. I knew that R4 was going to be 3 times higher than R1. So that'll be 750 milliwatts. I knew that R3 is half of R4. So that's 353.75 milliwatts. And I don't think there's an easy way to do R2. So R2 is going to be 0.05 times 12.5, 625 milliwatts. And again, if I add all those powers up, it should give me 2 watts. Does everybody see what I did there, or did I move too fast? Did I get going too fast and lose a bunch of you? Does that make sense? So like I said, this table is just a tool that I'm giving you to help you with the calculations, just to help you stay organized and to help you see. Okay, I remember it was a long time ago, but I remember doing this at first and thinking, oh my God, it's like 16 things we got to solve and I can't see what I have and I don't know where I'm going and I don't know what to solve for next. That with students is always seems to be the hardest part of doing these, solving these circuits. So if you can stay organized with a table where it's all laid out in a grid and you can see what you have and where you need to go, it seems to make it easier. The math isn't hard. Trying to understand what to do with it and where to use it seems to be the hardest part. Okay, I'm going to leave off there for today. We are 20 after and we work through our break. So it's really like more than 12:30, 12:35, something like that, because we went through our break anyway. I always set these classes up so that I've got enough time at the end for extra help, because it's easier for me to help you now when it's fresh in both of our minds than it is to do the class before the test, because it's too damn late then, doing it a day or two before the test comes. So if you don't understand, if I was moving too fast or it just doesn't make any sense, we have a half an hour to stick around and I will go through it with you until you do understand. If you do understand it, have a good weekend. There's no homework. We're going to do a couple of more of these series circuit classes to practice solving series circuits, and then I'll open up the series circuit homework. So no homework this weekend. If you understand, see you later. Enjoy your weekend. If you don't understand, stick around. I'm happy to go through it with you over and over and over until you do get it. Okay, see ya. You guys that are left, you got any questions before I sign off of here? Anything you need help with? last chance.